Hi, once again, this is the Tutor Wizard. This is Willa, and what we're going to do today is do some transition matrix and for the change of basis from one basis to another basis. You ready? Okay. Be quiet this time. Find the transition matrix S for change of basis from the basis E, which is V1, V2, to the basis F, which is U1, U2. And then if they say W equals 1, 2 in the basis E, write W with respect to basis F once you've done this. So the idea is we need to find the standard transition matrix S, and then we multiply S by this vector to get the coordinates in the new basis once we've found this transition matrix. So how do we find this? So from the scenario from the basis E and the basis F, I create two matrices, V, which is V1 as its first column and V2 as its second column, which is in our case 3, 2 and 0, negative 1. So that's V. Then we create U, not the vector, the matrix U, which is going to be these two vectors, U1, U2, which will be 1, 1 and 1 minus 1, which is of course U1 as its first column and U2 as its second column. So I create these two matrices from the basis E, I create column vectors, and I create a matrix V, and then I create a matrix U. It turns out that the standard transition matrix that we need is going to be U inverse V. If this is what the standard transition matrix is that we need every time, I'm going to require the inverse of U. For 2 by 2 matrices, this isn't so bad. Let's get to it. What the inverse? First of all, I compute the determinant. The determinant of this is negative 1 minus 1, which is negative 2. So the inverse is 1 over the determinant, negative 1/2, times, I switch the diagonal entries, 1, 1, and then minus 1, minus 1. This gives me the inverse U minus 1 of U. What I needed was these two matrices. Now we're going to multiply them, U on the left of V, to create the standard transition matrix. Therefore, S is U inverse V, which was U inverse was negative 1/2 times negative 1, negative 1, negative 1, 1, times V, which was 3, 2, 0, negative 1. Now we can either pull the negative out or clean this up. I want to put the negative in there. This will give me positive, 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 negative. So I just put the positive inside there quickly so that I can matrix multiply this. I'm going to leave the constant on the outside 1/2. So this is 2 by 2 by 2 by 2. So I'm going to get a 2 by 2 matrix. What is this? 3 plus 2 is 5. 0 minus 1 is negative 1. 3 minus 2 is 1. And 0 and minus 1 is positive 1. So this is the standard transition matrix S for change of basis from E to F is what we're doing. Therefore, if we're given W, which has coordinates 1, 2 with respect to basis E, to write it in with respect to the basis F, what we're going to do is write this as W with respect to the basis F will equal S times W with respect to basis E, which is going to be S is 1/2, 5, negative 1, 1, 1, times 1, 2, which is going to be equal to 1/2 times, now what are we going to get? 5 minus 2 is 3, and 1 plus 2 is 3, so we get the vector 3 over 2, 3 over 2. With respect to the basis F. This is the new coordinates. Alright, we're doing the same thing this time. We have a basis E inside R3 now, and we have a second basis F inside R3. I just switched those in there, but we're in 3 dimensions now, and I've been given a vector X in with respect to the basis E with coordinates 1, minus 1, 3. And we're going to do the exact same thing that we did with the two-dimensional case, except it's going to be much more work in the three-dimensional case finding the inverse and doing the computations. Otherwise, the scenario is the same. I want to find the standard transition matrix for the change of basis from E to F, and then I want to write X with respect to the basis F instead of with respect to the basis E. We need S, which is U inverse V. So I create these two matrices first. V we can compute readily. Then we're going to create U, but then we have to find the inverse of U, which is going to be much more difficult. I'll do both cases actually for the 3x3 to remind you of the scenarios that we have. So U is going to equal 1, 1, 0, 0, 1, 1, 1, 0, 1. Therefore, I have the two matrices that I need for these two bases. This is with respect to the basis F, and this is this matrix for basis E. To find the transition matrix S, this will be U inverse V. And then we're going to multiply S by W to get the coordinates with respect to the new basis F. Therefore, I need the inverse of U. Let's do that two ways. I can find the inverse by using the clever elementary matrix reduction where I write U block identity matrix and I row reduce to RREF and I get the inverse that way. Or I can use cofactor expansion and find all those. Let's do both just to remind ourselves. Method 1, to find the inverse of U using elementary matrices. Essentially what that means is I write U 1, 1, 0, 0, 1, 1, 1, 0, 1, block identity. Once I have that, I Gaussian Jordan eliminate to reduced row echelon form. That gives me, I'm going to get rid of this 1 here, so I get 1, 0, 1, 1, 0, 0. 1 minus 1 is 0, 1 minus 0 is 1, 0 minus 1 is minus 1, 0 minus 1 is minus 1, 1 minus 0 is 1, and 0 minus 0 is 0. I didn't change this one. Now I have a leading 1 and a leading 1. I've got to get rid of this guy. So 1, 0, 1, 1, 0, 0, 0, 1 minus 1 minus 1, 1, 0. 1 minus 1 is 0. 1 minus minus 1 is 2. 0 minus minus 1 is 1. 0 minus 1 is minus 1. And 1 minus 0 is 1. Now what we have to do is divide by 2 to get a leading 1. 1, 0, 1, 1, 0, 0, 0, 1, minus 1, minus 1, 1, 0. And then now we have some fractions. We had no choice. 1 half minus 1 half, 1 half. We're not done. We have to go all the way to RREF. So these two guys have to go. And we're going to get 0, 0, 1, 1 half minus 1 half, 1 half. Here I'm going to get 0, 1, 0, 1, 0, 0. So in the first move, we're adding. Minus 1 plus 1 is 0. Negative 1 half plus 1 half, or negative 1 plus 1 half is negative 1 half. 1 plus negative 1 half is 1 half. And 0 plus 1 half is 1 half. So we get 1 half everywhere, it looks like. Now we're doing subtraction. 1 minus 1 is 0. Why does that not look like a 1 half? Then I get 1 minus 1 half is 1 half. 0 minus minus 1 half is 1 half. And 0 minus 1 half is minus 1 half. This says that because this is now the identity, this is I3 block U inverse. So the inverse of U is the matrix 1 half, 1 half, negative 1 half, negative 1 half, 1 half, 1 half, 1 half, negative 1 half, 1 half. Hopefully you can see that I could take a 1 half out of that. But let's compute the other way just to make sure that we get that, and we should get the same thing. The other way to find the inverse is like this. 2. I can write all the cofactors. U inverse is 1 over the determinant of U times the cofactor matrix transposed, or the adjoint matrix. So let's build that. C11 is equal to, first of all, I need U1, 1, 0, 0, 1, 1, 1, 0, 1. C11 is equal to blocking off this and this, so that will be positive M11, and then that is going to be equal to 1. C12 is equal to negative M12, which is negative 1, 2, 1, 0, 0, 1, which is negative 1. C13 is equal to M13, which is equal to block off is 1, 1, 0, 1, which is equal to 1. C21, this is equal to negative M21, which is equal to, I block off this and this, so I get negative 1, 0, 1, 1, which is equal to negative 1. C22 is equal to M22, which is equal to, block off this and this, I get 1, 1, 0, 1, which is positive 1. C23 is equal to negative M23, which is negative the determinant by blocking off the second row and the third column, 1, 0, 0, 1, which is negative 1. Now for the last three, we're going to block off the third row and then the columns respectively. C31 is equal to M31, which is equal to 0, 1, 1, 0, which is negative 1. C32 is equal to negative M32, which is negative 1, 1, 1, 0, which is positive 1. And C33 is equal to M33, which is equal to this, the determinant 1, 0, 1, 1, which is equal to positive 1. Therefore, the cofactor matrix is equal to C11, C12, C13, and then the second row is these guys, negative 1, 1, negative 1, and then the last row is these guys, negative 1, 1, 1. Those are all the cofactors. That's the matrix of cofactors. Once I have the matrix of cofactors, I also need the determinant of U. The determinant of U is U11 C11 plus U12 C12 plus U13 C13, which is equal to U11 is 1 times C11 is 1 plus 0 times negative 1 plus 1 times 1, which is equal to 2. So the determinant of U is 2. And the cofactor matrix transposed is equal to, I'm going to transpose, so 1 minus 1, 1, minus 1, 1, minus 1, and then minus 1, 1, 1. Two negatives. This should not be negative. Sorry. In there. Method 2 is going to be, let's find all the cofactors of this matrix. First of all, I need C11 is M11, which is equal to, I block off row 1 and column 1, so 1, 0, 1, 1, which is positive 1. C12 is equal to negative M12, which is negative the determinant by blocking off row 1 and column 1, so 1, 0, 0, 1, which is negative 1. C13 is equal to M13, which is the determinant by blocking off row 1 and column 3, 1, 1, 0, 1, which is positive 1. C21 is equal to negative M21, which is negative the determinant by blocking off row 2 and column 1, so 0, 1, 1, 0. Row 2, column 1, yeah, which is 1. C22 is equal to M22, which is obtained by blocking off the Greek cross, so we get 1, 1, 0, 1, which is positive 1. C23 is equal to negative M23, which is negative the determinant obtained by blocking off row 2 and column 3, so 1, 0, 0, 1, which is negative 1. C34 1 is equal to M31, which is the determinant by blocking off the last row in the first column. So 0, 1, 1, 0, which is negative 1. C32 is equal to negative M32, which is negative the determinant by blocking off. So I'm going to get that guy 1, 1, 1, 0, which is 1. And C33 is equal to M33, which is obtained by blocking off this and this. So 1, 0, 1, 1, which is positive 1. Now that we have all the cofactors, I totally screwed up, and so I had to fucking start all the way over again. It was really aggravating. Now that I have all the cofactors, what am I going to do with all the cofactors? I have to put that into the cofactor matrix. Where am I going to squeeze that in now? Once I have the cofactor matrix, what I'm going to do with that is we need the determinant of U also. So this is the A11, A12, A13. This is C12, C12, C13. And the determinant, Cauchy says, cofactor expansion along the top row of U gives me the determinant of U, which is U11, C11 plus U12, C12 plus U13, C13. The U's are from the matrix. The C's are the cofactors which I just built. So now this is equal to U11, 1 times C11, 1 plus U12, 0. I didn't even have to compute, but I've got it. So negative 1. And then 1 times 1. So the determinant is 2. I also need the cofactor matrix transposed as the adjoint. The adjoint of U is the cofactor matrix transposed, which is now this, which didn't work the first time. We'll put it at the end of the video. I had a -1 wrong, and then it just threw me off, and I had to stop and get it. I'm a human. If you don't think that you're not going to make mistakes when you try to compute a million cofactors or something like that, you probably will. I had a minus error somewhere, and I could tell, so I had to start over. Let's see if we got it right this time. Transposing this now, this row becomes my first column, 1 minus 1, 1. This row becomes my next column, 1, 1, minus 1. And this row, it looks right now. I just have a minus here and here and here. And I do, so it makes me happy now. You can check by multiplying. But what was the point of this? I'm trying to find the inverse, which I already did using Gaussian Jordan elimination and row reduction, but I'm showing you both ways. So I have the determinant of U. I have the cofactor matrix of U transposed. Therefore, U inverse is 1 over the determinant of U times the adjoint of U, which is equal to 1/2. This guy's a number. Scalar multiplied by this matrix. 1, 1, minus 1, minus 1, 1, 1, 1, minus 1, 1. When you do that, you get what we got, and I found from the first way, you get exactly that. We're actually going to use this method, or I would want to factor the 1/2 out, because we're going to multiply this by this matrix now, and I don't want to multiply 1/2, 1/2, 1/2, 1/2. I want to do ones, and then multiply by this. Let's do that. To recap, we were given a basis E and a basis F. From basis E, I create a matrix V, which is the columns, the vectors V1, V2, V3 as its columns. Then we also created a matrix U, which has columns U1, U2, U3. From that, we found the inverse of U, which now the standard transition matrix from basis from E to F. The transition matrix is U inverse, the one from F, U inverse V is the transition matrix that we create. Now I have to matrix multiply, that's why I left the 1/2 on the outside. This will become now, it's a 3x3 matrix, multiplied by a 3x3 matrix. The inside indices match, and so it's well posed, and the outside will be the same size. So I'm going to get 1/2. This is what the rules say. If you're multiplying, just leave it on the front, the 1/2. That's what it's saying. A times B, U inverse times V. What are we going to get? A 3x3 matrix. I'm going to use my fingers to keep track. So the first entry is dot product this one with this. So 1 plus 1 is 2. Minus 2 is 0. 0 plus 1 minus 2 is -1. 1 plus 3 is 4. Minus 2 is 2, is the first row. -1 plus 1 plus 2 is 2. 0 plus 1 plus 2 is 3. -1 plus 3 is 2. Plus 2 is 4. 1 minus 1 is 0 plus 2 is 2. 0 minus 1 plus 2 is 1. 1 minus 3 plus 2 is 0. So I've done the matrix of multiplication. We can keep that on there also, but I'm going to keep it on the outside. This is the standard transition matrix for change of basis from basis E to basis F. And then the last thing I think they wanted from us was W with respect to basis E was 1 minus 1, 3. And it wants you to write this vector with respect to the new basis F. What I do is I hit this vector with this transition matrix, and it will give me the coordinates of F with respect, or with W with respect to the basis F. So W with respect to the basis F is S multiplied by W with respect to the basis E, which now I can multiply. If I move this, this will be 1/2, 0, negative 1, 2, 2, 3, 4, 2, 1, 0, multiplied by 1 minus 1, 3, which is going to give us 1/2 times, what are we going to get? 0, 1 plus 6 is 7. We're going to get 2 minus 3 is negative 1. Yeah, negative 1 plus 12 is 11. And then 2 minus 1 is 1 plus 0 is 1. So the new, you can multiply that in there, but the new coordinates of that vector W with respect to the basis F are 7/2, 11/2, and 1/2. This is how we do change of basis. Please subscribe below. He can do that in the editing now, but we're going to try that again. He just wants me actually doing it. So you need to subscribe below and hit the notification bell. You'll get a notification for when we make more videos on this. There will be many more videos to come. In particular, we're going to do linear transformations and a bunch of other videos. We're going to do everything basically, but my editor's slow, so he's gumming up the works.